the conditioning that you guys have over there.
Yeah, we are just reverse to you, nothing else.
Yeah, yeah.
You heat yourself and we cool yourself ourselves.
Yeah.
Good. Basically, it's a new topic for us, so it'll be interesting.
Hopefully it won't be soon.
Good, Abdullah. Thanks for your sponsorship details here. I think we can start. We got sufficient audience. Good evening and welcome to our CPD Talk of June month, which will be a little interesting topic, maybe different to our region. So, first of all, welcome to Julia and Orlando and for the how to calculate embodied carbon. So, just to brief about this topic, we as a global structural engineering firm or institute, we are planning to develop or already developing basically carbon emissions and how to improve the carbon calculations and guidelines, etc. We being basically the climate change. Earlier we used to be a very popular name. So that has transformed to climate emergency. That's what I know from last one and a half year. So the climate emergency is the one which we've taken up. So in 2019, Institute have established a climate emergency task group, which is working on setting up guidelines and standards and educating the structural engineering community across the globe. So we are a little bit lag in this aspect of it, maybe various reasons. We are catching up on this topic with our friends Orlando. So what happened as a operational carbon, we are very popular, as you know. Operational carbon means industrial emissions and etc. We very well versed, particularly automobile emissions, etc. Currently, we are looking for basically built environment how to calculate carbon. It's called embodied carbon. So accordingly, we are looking at standards. In the region-wise, we also set up some sort of a group to study this topic. Ms. Julia is leading our group for this topic and coordinating with the headquarters. And we'll come back with a certain regional group or region related information to the fellow structural engineers. So basically, coming to the engineers, what generally we think about, I always say, cost and time and quality. Now we need to think about another parameters called carbon. That is so important. And we, as an institution, we are thinking carbon as equal to a structural safety. That's what the direction for our planet, to make it working for long term for our future generations of the planet. Yeah. So that's about our background about our topic. To move forward, I welcome again Julia and Orlando from the both working in Arup only. So with a brief introduction, Mr. Orlando is specializing in embodied carbon at Arup and is group lead for sustainable and life cycle assessment subject, and is developing and working closely with the HQ team for climate emergency task group. Thank you, Mr. Orlando. Welcome to the board, and lastly but not least, thank you for our sponsor, our gold sponsor, Tech Assist and Idea Statica, who is a connection design and various software for the structural engineers. Thanks for your support for always for our institution. Today's maybe after presentation there will be a Q&A session, which Ms. Julia will take over on the question Q&A session, and there will be some survey. I'm sure it will be an interesting topic for all of us to move forward to have a better planet and better environment for our future generation. Orlando, the platform is for yours. Thank you again.
Good evening, everyone. We will just start the session tonight with a short poll. If Abdullah can launch the poll. It's a simple question, just reply yes or no, then we can move on.
I won't take part in this poll.
Okay, a few more seconds. Abdullah, let us know when you're ready to share the results.
We still have 5 need to vote.
Okay.
All right, it's ready.
Okay, so it will be interesting for most of you to discover how to calculate embodied carbon tonight. Orlando, to you.
Brilliant. Thank you so much to Sama, Abdullah, Julia, and the rest of the UAE chapter at the IStructE for inviting me to do this talk. So yeah, as been said, my name is Orlando Gibbons. I'm a structural engineer in Arup's London office, and I specialise in embodied carbon. I've been at Arup for 5 years, and I've done a number of secondments to various sustainability teams within Arup. I'm very involved with the IStructE, and I recently wrote a guide about this, which I'll tell you about during the course of this talk. And I've also recently just completed a secondment working with a team leading up to the annual climate change conference that this year is going to be in Glasgow. So there's a UK team working behind it that I was part of for a year, which is very exciting. Anyway, back to how to calculate embodied carbon. Okay, so this is what I'm going to take you all through today. So first of all, just going to start off with some terminology. There are lots of terms that are thrown around, and it can actually get really confusing, even for those people who know a lot about this topic. I'm going to go on why is embodied carbon so important. Then I'm going to go through the IStructE, how to calculate embodied carbon, and finish on the structural CO2e rating system, or scores. So terminology. So first of all, what is embodied carbon? Well, basically, when we have a building, we produce products, we transport those products to the site, we construct the building or the infrastructure asset on site. During the lifetime of that asset, there will be some maintenance and repair works, and then when that building or infrastructure asset has come to the end of its life, there'll be some processing of those materials to either recycle, reuse, or dispose of them. So at each of these stages, various amounts of material resources and energy get input into the system, and out the other end comes a load of waste and pollution, and also these greenhouse gas emissions. And it's those greenhouse gas emissions that we call embodied carbon. That's really related to the use of material resources and everything around it. And then another term that is really good to be aware of is whole life carbon. So whole life carbon is embodied carbon, which I just briefly explained, plus operational carbon. So operational carbon is the emissions released during the operation of your buildings. So that's heating, electricity, or in the UAE, a lot of cooling, and water usage as well. So whole life carbon is those two things added together. So this is how we normally visualize whole life carbon. and embodied carbon and operational carbon. We use these life cycle stages and modules, which are split up into 4 different stages. There's the A stage, there's B stage, and there's C stage, and lastly a D stage. So A is all about producing the product, transporting that product to site, and then constructing it on site. So that's the A1 to A5 there. And then the in-use stage, which is B1 to B5 in the pink, and then B6 and B7 in the yellow. That's stage B, which is all about during the use of the building, the different stages that happen there. So that's maintenance and repair that I mentioned earlier, and also all the operational carbon sits during the use of the building. And then there's the end of life stage, which is everything from taking the building down to transporting those materials away from sites, processing those materials, and disposing of them. And then stage D, which is sort of outside of the system boundary that we would consider for our building or asset, is what happens with those materials that are taken away from the site in their next life, essentially. So are they reused on another project? Are they burnt for energy recovery, or are they recycled and made into new products in the future? And the reason why that's a nice thing to look at as well is because we can then either tailor our designs to make sure that future projects use less emissions because they're already making the most out of those resources that already exist. And you might have heard of this principle called circular economy, where the idea is basically keeping products and materials at their highest value. So it's a good metric of that. So as I said, you can see this kind of blue dashed box is whole life carbon. That encapsulates the pink, which is embodied, and the yellow, which is operational. And then the embodied carbon is stages A to C. And then within those stages, you have these modules A1 to C, A1 to A5, B1 to B5, and C1 to C4. So that's a really good diagram to get familiar with on this topic because it's referred to a lot. And then lastly, you might have heard of the term net zero carbon, and there's lots of confusion about this, and really this term is still being properly defined in the industry, even in a part of the world where embodied carbon is a relatively mature subject to talk about. It's still in its infancy, but compared to lots of other places in the world. But net zero carbon is basically where the emissions associated with some activity plus any offsets. So by offsets, that means that anything that's either sort of taking greenhouse gases back out of the atmosphere, so reducing the amount of greenhouse gases in the atmosphere either by sequestration and storage, or it can mean by kind of replacing a business as usual method of doing something with a much lower carbon method of doing something. So there are a few different types of offsets. To be honest, offsets isn't my speciality, so apologies if that's wrong, but it's when those two things balance and equal zero. So basically offsets that you can think of as like negative emissions, and emissions is obviously any emissions getting released into the atmosphere. Obviously with that, when we consider net zero's tendency to think, okay, I don't need to worry about emissions so much, I can just have loads of offsets and then that's a good job done. But really we need to make sure that when we consider net zero carbon, that emissions are minimized as much as possible, because that's the most important thing. Offsets won't always be available to us as we hopefully use less and less energy. So offsets should really be a last resort. And lastly, carbon is sometimes used as a common term for carbon emissions equivalent, which is basically any greenhouse gases such as carbon dioxide, methane, and water vapor and others normalized to the same global warming potential as carbon dioxide. So by global warming potential, it's basically the ability of that gas to trap heat within the Earth's atmosphere. So why is embodied carbon so important? So as we've all heard, I hope, global temperatures are increasing. This is kind of a sketched version of a graph from the IPCC, International Panel on Climate Change. And it shows temperatures across the globe steadily increasing. And you might have heard 1.5 degrees C. We're trying to keep below 1.5 degrees C, but at this stage, where we are now in 2021, it's looking pretty inevitable that we'll get there. So, but we really need to make sure that we don't go past 2 degrees C, because that does a huge amount of damage through changing the way that our climate works. So in terms of the impact that getting to 1.5 and 2 degrees C have on the planet, you can see here. But when we get to 1.5 degrees C, sea levels will rise by 0.85 meters. Corn and wheat yields will reduce by 10%, and there'll be a lot more heavy rainfall over land. When we get to 2%, which is considered kind of the safe limit of ecosystems and civilizations as we know it, still a huge sea level rise across the planet of 1 meter. Some cities will start to drown, such as Amsterdam, low-lying cities. Corn and wheat yields even worse, and you get the idea. So the further we go beyond these points, the more drastic the impacts on our lives as we know it will be, and also on ecosystems and biodiversity around the planet. And based on the carbon budget at the moment, when we're thinking about how much carbon we need to release in order to get to this 2 degrees C warming, that at the current rate of emissions, that is only 8 years away. So that gives a real sense that we need to do so much more than we are currently to change this around, to make sure that we're not impacting everyone on our planet and future generations. So what do we need to do? So here you can see, as our careers have been going along, emissions have increased, as I've already talked about. And basically post-2020, we need an extremely sharp decline in the emissions that we're releasing. And that this graph is from the IPCC, and that's without carbon capture and storage. So to do this, we need rapid, far-reaching and unprecedented change. And where does embodied carbon fit into this? Well, it plays a huge role. So as you can see from this pie chart, the construction, so materials used in the construction industry, which is essentially embodied carbon emissions that we're thinking about, accounts for 11% of global CO2 emissions. That's more than aviation and other really carbon intensive industries. So we have a huge role to play as structural engineers. And this graph shows that actually, when we think about new build developments, because there have been quite a lot of efforts in various places around the world to reduce operational emissions. Actually, by the time we get to 2050, which is kind of the target that everyone has set to get to net zero, governments have set to get to net zero, and the UN and the kind of intergovernmental climate change panels have set to get to net zero. Half of those emissions from new builds will be from embodied carbon. So we have a huge role to play. And StructE accounts for a very, very large portion of this. So as you can see from these two charts, the superstructure accounts for almost 50% of the embodied carbon of our buildings. And that's those emissions that are released by practical completion. So as structural engineers, we are responsible for a huge portion of that 11% I mentioned earlier. And then if we think about this compared to our own personal impacts in our personal lives, if we look at some of these figures about things that we might do. So speaking from me, so this is one return flight from London to New York in economy. If I don't do that, I might save 1,000 kilograms of CO2. If I cut meat, dairy and beer out from my diet, I might save 2 tons of CO2 every year. If I stop driving my car around 10,000 miles, I'll save 3,000 kilograms of CO2 per year. But if I make sure that on every project I work on, I reduce the structural embodied carbon by 20%, that would equate to roughly a saving of, from my impact personally on my projects, 200,000 kilograms of CO2 per year. So that kind of shows the scale of the impact that we can have as structural engineers on reducing emissions. So basically, as simple as this, we need to do everything we can to minimize embodied carbon of all of our projects everywhere in the world and we need to do it now. And we can do it. Studies have shown that we can achieve up to 50% savings if we rethink the way that we design in some cases and put more thought into it. And really, to understand how to reduce embodied carbon most effectively, we need to know the numbers. We need to understand what the embodied carbon is in our projects and where it lies in our structures. So this really prompted, this is what really led to producing the guide on how to calculate embodied carbon, which is freely accessible on the IStructE website for anyone. And I'm going to talk about it more now. So why do we write it? Well, to provide a common calculation method in places where embodied carbon is calculated, it can be done in slightly different ways, and there is some ambiguity about what should be done. So this was to provide some consistency. And by doing that, by making sure that everyone's calculating it consistently, then we can actually start to compare designs against each other, because comparing two different things that are done differently just doesn't make any sense. We calculate embodied carbon to improve our understanding of it. We understand where it typically lies in our structures and how we can reduce it and support material demand reduction, and to help us find new ways to reach net zero, which is one of those terms that I mentioned earlier. So I wrote this guide in collaboration with Dr. John Orr from the University of Cambridge. And we obviously had the help of many people who provided fantastic comments and input. So thank you to all of those people. It wouldn't have been possible without them. So there are some key principles from the guide. Firstly, that we need to get to net zero by 2050. Secondly, we need to do this on all of our projects. We need to calculate embodied carbon. Thirdly, we need to recognize carbon as just one metric of sustainability. This diagram here with the multicolored diagram shows it represents the Sustainable Development Goals, and carbon is just one piece of that puzzle, but a very important piece. We need to evaluate design decisions against their carbon impact. So we need to consider every design decision, how much emissions it has associated with it. We need to communicate this to the design team so that we can work together with the other disciplines to reduce carbon emissions. And then, of course, we need to reduce carbon emissions, as I just said. And lastly, we need to report these findings from our projects. We need to share this data so that everyone as an industry can learn more and push carbon reductions further. And then this is something that we've done in the guide. So I'm sure you can go on the IStructE website and type in how to calculate embodied carbon and come up with the guide. And within the guide, there are some sort of things that we've done to try and make bits of information clearer to the reader. So we've made some suggestions, hints, and common pitfalls and tips. In the red box, in the green box, we have key principles, and in the grey boxes, it sort of highlights what you have at the end of a part of the process. So the structure of the guide is we have inputs to the calculation, we have the process, and we have the output. So it's basically it's structured around that very simple idea. And this is the sort of flow diagram that we use to describe the different parts of the process. So as I said, inputs on the left, process in the middle, and outputs on the right. And this inputs and process bit, there is some any good consideration of embodied carbon should iterate between these two bits. So because the data that you have and the inputs that you have will develop in their accuracy as your project goes into the more detailed design stages. You'll want to update those inputs to refine your carbon calculation. And something that's definitely worth mentioning, and I encourage you all to search this on your internet browser as well. In March, the structural carbon tool was released, and this is a project between the IStructE and a design consultancy in London called Elliott Wood. It's a fantastic tool. It's Excel based, very easy to use, access it from the website. There are video tutorials on how to use it. It currently contains mostly kind of UK relevant data, but you can add any data you want to it, so anything that's more relevant to the UAE. And it's basically the How to Calculate Embodied Carbon guide in Excel version. So basically, it distills the guide, brings it into an Excel, and it allows you to get on with it much quicker, which is brilliant. So, how to calculate embodied carbon. So throughout this, I've got a sort of worked example that I'm going to be going through. But I think, I might try to go through it relatively quickly because I want to leave time at the end for questions. So this project, this imaginary project, is in London, commercial building, 56,000 square meters, construction cost of £120 million. The roof extension, which had CLT, which is cross-laminated timber on a steel frame, side extension of some concrete with some new foundations, and also a refurbishment of an existing building. So first thing we need to think about is, what is the scope of our calculation? So these are the life cycle stages that I discussed at the start. This is the first thing you need to consider is what is the scope in terms of life cycle stages. So the minimum scope that we say in the guide that you should consider is A1 to A5. This is the minimum. You shouldn't consider less than this, but considering more than this is better. So if you were to consider all of the life cycle stages, so from A to C, including module D, then that is kind of the ideal scenario. But appreciate that a lot of people coming new to this topic, actually focusing on A1 to A5 is best. It's where we have our highest impact, and it also simplifies the calculation a bit. So why do we use A1 to A5 as a minimum? So that A1 to A5 is basically material extraction all the way to practical completion on site. So when the building's finished and just before people are about to move in and start using it. So A1 to A5 emissions are all released by the time the building is being used. So they will be released before 2050, which is our deadline for getting to net zero. We have most certainty over A1 to A5 emissions data because it's happening closer to the time that we're actually in right now. And the majority of structural embodied carbon is in modules A1 to A5. And then in terms of minimum scope, in terms of building elements, so there's the life cycle stages we consider, but also which parts of the building are we thinking about. This table here is from a Royal Institute of Chartered Surveyors guide. And if you just pay attention to the right-hand column, this kind of gives you a list of the things that you should be including in your embodied carbon assessment. So it's basically anything that you would design as part of your structural engineering scope, including the assessment, as well as the foundations, because as you know, the foundations are dictated based on the structural system that sits on it. So as I said, include whatever's in your scope of works. Consider other elements dictated by the structural system. So for example, you should consider fire protection because fire protection is something that provides a structural function. It makes sure that the structure retains its structural integrity through different scenarios. You should coordinate the scope with the rest of the design team. So if the architect's also looking at embodied carbon, make sure that you coordinate with them so that you're not both duplicating work, but also doing it all consistently. And then identify interdependencies of building elements. So think if you are increasing the depth of your floors, what effects that might have on the facades, or if you're using exposed concrete rather than steel that's protected with fireboard or something, think about what that might do to the ability for the building to store thermal mass and reduce operational emissions. So those are other things to consider alongside embodied carbon. So the fundamental principle is probably the simplest calculation you're going to do on your project. So you calculate your quantity of material, which we do in design anyway, and you multiply it by a carbon factor. And you basically do that for all projects used at each stage of the life cycle. So obviously, for quantities, numerous ways to do this, and it depends on design stage. You'll have your own way of doing it. Maybe it's we'll come on to that in a second, actually. And for carbon factor, there's a different carbon factor for each life cycle module, A1 to A3, A4, A5W. Those are the ones that we're going to be looking at. So for our make-believe project, we'll be looking at A1 to A5, which I mentioned earlier. So think about the inputs now, which are material quantities and embodied carbon factors. So the inputs to this calculation. And on the process diagram, this is where it sits. So first of all, material quantities, you can get these from a number of places, as I said. Just make sure it's appropriate to your stage of design. So it can be from scheming manuals, so sort of rules of thumb. It can be from your previous project experience. You might have worked on a similar project and you know kind of what the kilogram per meter squared of steel was, or the reinforcement rate that was used. You can obviously do your own manual calculations. You can use a quantity surveyor's cost plan, or a cost consultant, as it might be referred to over there. Use your structural analysis models to generate the quantities, or use your building information models to generate the quantities. But make sure that if you are using some sort of modeling software to get quantities, that you also include partially modeled or unmodeled elements. So for example, something that's normally not modeled in building information models is reinforcement within concrete, or the fire protection, or the damping, the screed, for example, that's helping to damp the vibrations of your floor system. So just in this example, so let's say we're at stage 2, so we have no developed BIM modeled. So I did a manual quantities calculation, and I used a scheme design manual to get quantities for representative elements. And these are the kind of, so I've just laid out the quantities of my different materials and any assumptions that I've made. And one of the things you really need to bear in mind is that, of course, in the early design stages, we don't have perfect information. We don't know exactly what's going to happen at the end of the project when it's actually built. But do not let this deter you from calculating embodied carbon. The uncertainty in quantities will decrease over the course of the product, and you can update your calculations to reflect this. But if you miss the opportunity to calculate embodied carbon and see how you can reduce it in the early design stages, you lose a huge amount of the potential to reduce carbon. So in terms of the guide provides this information. So it has for each lifecycle module recommended values. It provides guidance for key structural materials, and it references the RICS guide, which is kind of the UK best practice standard for calculating embodied carbon. It is UK focused, but we do reference data from elsewhere in the world where it is available. I think Julia is going to help us out with that later on. So carbon factors for modules A1 to A3. They're very dependent on production method and location. So take that into consideration when you're choosing which ones. Again, do not be deterred from calculating embodied carbon from uncertainty in these factors. Supply chains are very complex things, and it will be very difficult to have precise information on the emissions of your materials. But what you need to do is you need to think logically, what is my best guess at this? And you should proceed on that basis. So the way that we split this up in the guide is we consider first whether, do you know what the specification of your material or product is? And we start off with, if you don't know that, so this is normally at the early design stages, we've included a table within the guide that recommends typical values to be used as a starting point. But if you do know your product specification, then you need to ask your manufacturer for an EPD. An EPD stands for Environmental Product Declaration. There's this image on the right is an example of what one of those might look like. And it basically gives environmental impact information for a product or material. Ask your manufacturer to create the demand. It's really good for manufacturers to know that people want this. It will help to push the industry forward. So Julia, can I invite you to jump in here?
Yes. Okay, so we just talked about EPDs. And we must say that for UAE, we do not have a comprehensive carbon factors library, nor for any countries in the Middle East that we are aware of in our IStructE regional group. But there are APD available for lots of material like steel, rebars, concrete, precast, and they are region-based. For example, you see the UAE flag on the one on the left side, you see Dubai precast on the one on the right side. So this information is available. You will not find it in a specific location, so you will have to go around the internet a bit. You can find it on the Dubai municipality, on the Green Book Live. Another website is EnvironDeck, or you can refer to the Emirates Green Building Council website, and they have a link to a tool that is called One Click LCA Planetary, where they have a small library of UAE materials. So the information is scattered, but the more you use it and the more you request it to suppliers, the more information that will be available for everyone to use. So it's very important to increase the demand and to use this information and do your calculation to increase the awareness in the region.
Absolutely, thank you, Julian. I don't know whether you can't see it because I've got a background on, but I was holding up the guide, a printed version of the guide, and the guide has in it a list of websites that you can get EPDs from. So you can it's on page 14 of the guide, and you can use that as a starting point, and it includes some of those that you just mentioned there, Julia. Thank you. So just quickly looking at some of the key materials. So concrete. So concrete is made up of cement, sand, aggregates, water. Really, the thing that the constituent of concrete that dictates its embodied carbon is the cement. So as you can see from this pie chart here on the left, this is a breakdown of embodied carbon by concrete constituent, and you can see Portland cement for this particular mix and strength, which is C3240. Sorry if that's not how you refer to it in UAE, but it's almost 80% of the embodied carbon is from Portland cement. So really, when you're using concrete, think about how you reduce the cement content to reduce the embodied carbon. So that can either be done using a lower strength concrete, or you can use cement replacements, such as GGBS, which is a byproduct from the steel making process, or PFA, which is a byproduct from the coal burning process. And this chart on the right here shows variation in embodied carbon of concrete. So because you can have so many different, you can have a completely unique mix of concrete on every project, it can vary quite a lot. So there's a lot of opportunity to either have a really green concrete mix or a pretty energy intensive concrete mix. So for steel, there are a number of different, so steel embodied carbon really depends on production route and the scrap content within the steel. So the two main routes, and I'm not sure if you can see the highlighted yellow, is the BOF route and also the EAF route. So those are the two main ones. The BOF one uses natural gas, oil or coal and not very much scrap content. The EAF method uses electricity and lots of scrap material. So it's generally much lower embodied carbon. As you can see from this graph, this is ranges of embodied carbon for steel produced in different ways. There's a huge amount of variability. So that's why it's good to understand how the steel that you typically use in the UAE is produced. I've marked on this graph a couple of EPDs that we use in the UK and in Europe to work out the embodied carbon of steel. And then timber. Timber is a really interesting one, and we can talk for a long time about this, so I'll try not to. But as you know, as timber grows, through photosynthesis, carbon dioxide is taken out of the atmosphere and stored in the tree in order for it to grow. So this kind of red line that you see creeping up on the left-hand side here is that sequestration. When the tree is cut down, typically only 50% of the stem is used for the construction, and typically the other material in the crown and other parts of the stem are used in other industries. And then at the end of the life cycle of that piece of timber, that carbon will be released back into the atmosphere in one way or another. So this graph shows the carbon stored in the timber product over its lifetime. And there's this equation at the bottom is kind of typical amount of sequestration per kilogram for a timber product, and so you can use that as a default. And this is an interesting one because there are rules as to when you include sequestration in your calculation. So sequestration, you get a negative number, but you shouldn't include it in your A1 to A5 scope. So if you're just considering those emissions released at the start, don't include it. But if you're considering the whole life cycle, then you can include it. And I think we could do a whole nother webinar on that, which would be great, but I'll move on for now. And whatever you do, just be clear about what you've done. So this is for Project X, I've got all my materials and I've got the embodied carbon factors for A1 to A3. Then think about modules A4 and A5, the construction process. So for module A4, basically you calculate the emissions associated with the transport. You multiply transport distance by a transport emission factor, and you can most likely get those transport emission factors from either from a government website. So in the UK, we have a government website that has these factors, and that's what's included in the guide. But there are international factors as well that actually, in the update of the guide that is going to be released later this year, some more international representative transport emission factors to be used. And then at the bottom here, you can see a calculation that I've done for this make-believe project that shows the transport distance multiplied by the carbon emissions the transport emission factor for the different materials, and then you add those up, and then that gives you your A4 emissions. So for A4, really good things to do to get better accuracy is to ask the manufacturer for predicted logistics. Estimate your transport distances based on project-specific scenarios. So you know if your concrete's being produced in Dubai and your project's in Dubai, you're going to have a pretty good idea of what your transport distance is. So you can adjust it. Whereas if your steel is coming from somewhere in China and it being brought to the UAE, then you can also make a judgment as to how that material is being transported there. So going on to A5 now. So A5 is the actual process of installing constructing the building on site. And this is kind of broken down into two areas of emissions, one of which is the emissions associated with the production and the end of life impacts of the materials wasted on site. Whereas the A5A is a site activities, and that's really on-site electricity consumption and fuel usage. So that'll be from machinery like diggers or cranes and site huts as well. So where the workers are sort of doing their work next to the site, all of that's in A5A. So the life cycle emissions of materials waste, sorry, this might look like a bit of a daunting equation, but so ECF stands for embodied carbon factor, and waste, this WF factor here, that stands for waste factor. So you're basically multiplying the embodied carbon of all of these different stages, so A1 to A3, A4, C2, and C3 and C4. So these C1s are the end of life embodied carbon factors. You're multiplying it by the amount of, by the fraction of materials that are brought to site that are wasted. There's a little calculation to work out what this waste factor is. We've done this for you in the guide, shown there in the table. And in order to get a better understanding of these material wastage factors, recommend making it a requirement for your contractor to collect waste data for different products and minimize waste rates during construction as much as possible. I'm going to skip over the site activities because we don't have much time. There's also a load of information on stages B, C, and D, which is all in the guide, but we won't have enough time to do that now. So in summary, collected inputs for the project X, and then we go into the process. So the actual calculation stage. So as we went through before, we've got the simple principle of quantity multiplied by carbon factor. And then this is just an example of a spreadsheet that I had used before, where I've got all of my quantities of materials for my different building elements, and I've arranged them embodied carbon factors by different stages. And then I've used just simply with Excel to show me where the hotspots are. So the darker red numbers are sort of the higher embodied carbon. So you can see my superstructure, upper floors, beams. That's where the majority of my embodied carbon is sitting. And then that's a kind of a quick way of showing the overall numbers. And this is it plotted on a graph. So from this, you can see how powerful it is in identifying the carbon hotspots and where you should focus your carbon reduction efforts, which is beams and the slabs. This is an example of a project that I worked on where we considered different options. This one, we actually, instead of building a new building, we just the client decided to refurbish the existing building and extend it, which saved a huge amount of carbon. So this is really an example of where refurbishing buildings is way, way better than building something from scratch in terms of carbon emissions. They say 52% embodied carbon. And these are just some other options. These are other examples of where different structural systems have been assessed based on their embodied carbon that inform the decision-making process. And another thing that you do, so once you've calculated the total carbon emissions, you normally normalize it by the, if you're in a building, by the meters squared of that building, by the area of that building. And then crucially, you in order for this to inform the design process and what you're actually going to do on your design, you've got to share it with the design, communicate it to the project team. So regularly communicate it and be transparent about it. And you can do this through a workshop or just through general advocacy. And in reports and drawings, just always good practice to include something about the carbon emissions associated with your project. And then once you've done that, once you understand where your embodied carbon hotspots are, then you can think about reducing it. This is a framework that we use quite a lot for thinking about how to best minimize embodied carbon. That starts with building nothing and advising your clients how they can make best use of the existing assets. Building less, so advising how they might be able to reuse parts of it and maybe extend bits of it in order to maintain the same value. And this all still requires structural analysis work. So this isn't like we're completely out of jobs, but it's just providing information and expertise to the client that will allow them to do something with their existing assets. Building clever and efficiently means really thinking about the materials you're using and minimizing the use of those materials. And based on the different design stages that you're at, really you can have the biggest potential for carbon reduction at the early design stages of the project. And that kind of decreases as you go along. So, and of course, as I said earlier, best way to find out how to reduce embodied carbon is finding the hotspots on your project. And there will be a guide released soon called Design for Zero for the IStructE, so look out for that. And then outputs, I'll very briefly touch on this, but reporting and sharing this information is really going to help the industry in your region push forward and understand how to do this across more projects, raise awareness of it. And also it's crucial, once you might have done this all throughout design stages, but you need to do it at the as-built stage as well. So you need to work with the contractor to understand what the emissions are when it's actually built, because we might have ideas of where the materials come from during design, how much, what the quantities of materials are, but really once that building is built, it's there, and it has a certain amount of embodied carbon. We need to find out what that is so we can find out whether our design assumptions were accurate and also so we just know what's going on. Otherwise, we're still in the dark on this topic. And share case studies. And just very quickly, so I know we've only got 8 minutes left of the session, but very quickly, there is a rating scheme as well called scores that a few of us at the IStructE came up with, and that basically kind of gives a range of what embodied carbon looks like on a project, and it gives you a letter rating for your embodied carbon based on your kilograms of CO2 per meter squared. That range was defined by a number of different firms, including Arup, Thornton Tomasetti, and Bureau Happold, who gave some data. We looked at the different embodied carbon, and this was kind of the range. So that informed the A to G rating. And then really this is the, we can think about this, getting to net zero, minimizing embodied carbon as much as we can towards 2050. This might be the trajectory that we're on. And some key messages. So when should you calculate carbon? The earlier the better. You have way more influence. Calculate it at every stage of design and construction. Calculate it whenever you have a design decision to make that may inform that design decision, and do it on every project, because we don't have time to not be thinking about this, because it's going to affect us all sooner or later, and it certainly will affect the next generation. It's the first step to addressing the climate emergency. And next steps, just quickly to let you know, an update to the guide is coming. So it's a very fast evolving area in the UK and beyond. I know that some regions are further ahead than others, but so we're looking to really keep this guide up to date. So we'll be relaunching a version 1.1 later this year. And you can find the guide on the website, and there's also a brief version of the guide that was released in the Structural Engineer magazine last year. Thank you very much for listening, and I'd be delighted to take any questions. I'm sorry there's not much time left, but I hope that's given you a good overview.
Thank you very much for the great talk, really. It was very informative, and I hope it will be very helpful for many of us. Start with one question is, since we are at the early stages in the UAE for embodied carbon calculations, and what is your advice that you can give us to accelerate this process and catch up with other regions?
So that's a great question. I think everyone needs to take some initiative with this. I think pretty much everyone, I imagine, appreciates what a beneficial impact this can have on the planet. And even if our clients aren't yet asking us to do this, I can assure you that they will be soon, because it's something that is spreading across the globe. So I think take the initiative to understand it now. Speak to your clients about it. Let them know what it is. Speak to your colleagues about it. Try it on your projects. Just do a quick carbon calculation on your project. Get the material quantities. Find a carbon factor using the information that Julia provided, and start from there. Work out, even if it's just comparing two different beams to get an idea of the difference in carbon emissions. And even that can be so helpful to helping you make those first reductions. And then, of course, during the construction stage, you need to speak to the manufacturers, speak to the contractors, and demand embodied carbon data information from them for the products that you're going to be using. They need to know that it's in demand for them to start producing the information that we need to calculate it more accurately.
Good, thank you for your reply. We have one more question. In this region, especially around Dubai, many projects have made use of a good number of existing piles, and due to various reasons, they were abandoned projects. And how can we quantify this into our calculation?
that's fantastic. First of all, so when you're doing a structural calculation, the minimum scope should be superstructure, anything above ground, plus substructure, or anything below ground. Excuse me. So a typical value of embodied carbon per meter squared might be, say, 350 kilograms of CO2 per meter squared. And that would be including foundations. So if your project already has foundations and you're not creating any more embodied carbon emissions to produce those, then that will be reflected in your total structural embodied carbon. So it might be more like, say, 200 or 250 kilograms of CO2 per meter squared. So that decision to reuse the foundations will be shown in the lower embodied carbon figure per meter squared for your building.
Thank you. Then we have a note from Ladin Kamchi of CARES is on the line. He has mentioned that CARES sector average RPD are specified in the IStructE guide for steel bars, and they are working on PC wire and strands and this product group. So it's not a question, it's just a message.
Hi, Ladin.
Yeah.
No, CARES are doing great work in trying to make sure that carbon emissions of all their products are tracked, and that they're trying to improve their digital tracking of their products as well, which is really good.
Yeah, we had the pleasure to host them for a talk earlier in the year. Yes. And another question, I think this is a clarification on the concrete slide. Based on the EPD data provided in the slide for concrete, it seems embodied carbon is reducing even if strength is increased. Any reason?
No particular well, maybe the reason is that cement replacements have been used.
Yeah.
Maybe it's the case that in lower strength concrete, too much cement is used where it's unnecessarily used. So maybe if you are specifying a low strength concrete, make sure that the concrete contractor or the contractor is actually using low cement content. It also might be because cements of lower grades might still need a certain level of cement content to, concretes of certain grades might need a certain level of cement content for durability requirements or other requirements if they're in extreme conditions. So that could be another reason. So of course, carbon is not the only factor to consider when designing your concrete mix. You need to consider all of the other factors along with it. So there can be variability in that, but especially if it's internal and isn't exposed to the elements, then there is no reason why you shouldn't be more ambitious about lowering your cement content.
And another question is about FRP and fiber reinforcement polymer has one of the least embodied carbon value, but is an expensive material at the moment. And are you aware of any development? I'm not sure towards what direction. But do you want to say anything about the FRP at all?
Yeah, I must admit I don't know much about FRP embodied carbon at all. Just because we need to. I've been focusing on steel, concrete, and timber as the kind of three key main materials being used. There's plenty to get our heads around in that. But yes, we should understand all of these materials better. Unfortunately, I'm afraid that I don't for FRP at the moment, but I hope to learn more.
Further studies are required.
Yes, further studies.
Okay. There is another question about digital twins. Many thanks for the very informative discussion. Will the digital twin-based project reduce the emission of embodied carbon? Are there any digital twins tools available to calculate embodied carbon? I think it's a bit of a specific question, but
so I think I mean if my understanding of digital twins is correct, I think the main benefit of digital twin is that you know what's in your current building, so you can better understand when it's coming to its end of life, which materials are there, which materials can be reused or recycled, and which materials might need to be repaired during the life of the building. So really, it definitely can help reduce embodied carbon. It might not help reduce the embodied carbon that's released at the start of the project. So those emissions that we call upfront carbon emissions that are released up until the project is completed. But it can certainly help to increase the provision of reused materials for future projects. Make sure that if it's used in the right way, of course, it depends how that digital twin is properly used. If it's there's a maintenance structure that makes sure all of the materials are properly maintained throughout the life of the building too. I hope that answers that question.
Thank you very much. I think that's all. I don't know, Sama, do you have any question?
I think I got only one question. So, I'm sorry, I am taking the question online because I'm privileged to take maybe. So you're calculating embodied carbon, but do you say you are giving any limitation to say concrete building will be this much or timber will be this much? Do you have any limitations, or otherwise you just calculate and that's it? What is your direction to the industry? You should not increase overall square meter embodied carbon equivalent should not be say 200 kg, or do you have any something like that, or what is the limitation for that?
So we don't currently have kind of targets that are for structures that are mandated. I think the development in that regard, Sama, is that we've produced this rating scheme that I mentioned at the end. And what that really does is kind of allow projects to see how good they are. I mean, the sort of A plus to G scheme, kind of like the kind of grades that you might get in an exam. That's kind of representative of how good the design is. So no targets have been set yet, partly because there, at the time of creating that rating scheme, there hadn't been enough project data submitted to really inform what that target should be. I mean, really, we need to be, in my mind, I have like pushing towards 150, between 100 and 150 kilograms of CO2 per meter squared would be like a really, really good design. I think anything below 200 would be fantastic as well. And I think those are kind of in the B to A ballpark for the scores rating scheme. But yeah, anything over 500, which is basically any high-rise building, because high-rise structures are really carbon intensive on the structure because you need lots of material in your columns and foundations. And so yeah, it's sort of to show what type of project is low carbon, and also, yeah.
Thank you, Orlando, for your valuable information on how to calculate embodied carbon. I think soon will be better experts and more engineers available in the region with available data. Yeah. Thank you. Thank you, Julia, and thank you, Orlando. And in the last few words, actually, from our region, I request all our members or structural engineers to visit the website IStructE.org and Climate Emergency, which is has got all the publications whatever developed from last 1.5 years. It is free. Almost it's free. Am I correct, Orlando?
Yes, it's this. All of this guidance. The tool is free. The guide is free. Yeah.
Yeah, it is a very good opportunity. Soon, when it's established, I'm sure it will be a price on it. You know. So it is
I hope there's never a price on it.
Okay. So that's what my request. And thank you very much. And thank you for our gold sponsor, Tech Assist and Idea Statica, for this opportunity for us to meet on this platform. Thank you one and all. We'll meet next month in another topic of CPD. Okay. Thank you, Julia. Anything? Thank you, Mr. Abdullah is there? Okay, he's not there. Yeah. So Abdullah is the brain behind the technology for us, you know. So thank you. Thank you, Orlando. We'll meet soon. And last question: will you share this presentation to people? Anybody ask, or will you share the presentation? This presentation.
Yes. Yeah, I'm happy. I'm happy to share the presentation.
Yeah, please share so that
you have recorded. You've recorded this session, have you? Though.
Yeah, we recorded,
Yes.
but if somebody wants to have some reference, anyway, a lot of information is there in the IStructE website as well.
Yes.
Something helpful. Thank you.
Thank you all and good night.
Good night.
Thank you, everyone.
Bye.